Good afternoon. Welcome to SCA's webinar with Dr. John Foster. He'll be speaking on Energy Data Science in Python, Introduction to Pandas. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. So I'm going to be launching some polling questions. And the first one is about your primary discipline. So it looks like we have quite a few geoscientists and petroleum engineers in the audience. The answers are come in. It's roughly half and half. Looks like most of you have voted, so I'll close the poll and share. 53% geoscience, 42% petroleum engineering, and 53% other. 3% other. So now I'll go to the next poll and tell us how many years of full-time experience you have in the oil and gas industry. Looks like we got a good distribution today. There's someone in every category, from less than 1 year all the way to more than 30 years. Most of you have voted, so I'll go ahead and share those responses. Looks like the largest group is in the 11 to 20 year demographic with 43%, and followed closely by the 1 to 3 year demographic, but someone in every group. So thank you for that. So I'd like to remind you that before I introduce John, I want to remind you that you'll be muted during today's webinar. And so you can ask questions using the GoToWebinar question feature. And we'll generally cover those questions at the end, and you will be anonymous. And so please be typing your questions throughout the webinar. And again, this webinar is on Energy Data Science in Python, Introduction to Pandas. Dr. John Foster is CTO and co-founder at Datum. He's a professor at UT in both petroleum engineering and in the aerospace department and engineering mechanics. And he also worked previously at UTSA in mechanical engineering and also has been involved at Sandia National Laboratories. John has his BS and MS in mechanical engineering from Texas Tech and PhD in aerospace from Purdue. He's registered as a professional engineer in the state of Texas. For SCA, John teaches Introduction to Energy Data Science in Python. So this class is offered in a public venue coming up in August. It's 5 mornings, 8 to noon, and you can see the outline of the class there. This is being offered live online, so it's a virtual delivery, so you can take it in any part of the world without having to travel to take the class. Here's a little bit more information about contact information if you're interested in scheduling yourself to attend this live online class, or perhaps you'd like to bring it in-house for your company. Just let us know. And John's colleague in Datum is Dr. Michael Perch. He also offers a class through SCA that's Introduction to Subsurface Machine Learning with Python. That's coming up soon, so we'd like to close registration for that at the end of this week. So if you're interested, please register soon. And just to remind you, SCA is available to help you with consulting, direct hire, projects and studies, and training. And so without further ado, I'm going to pass the presentation rights to Dr. Foster. Let me do that. And it's all yours. Take it away.
Thank you for the introduction, Susan. Can you see my screen well?
Yes, looks good.
Okay. Perfect. So Susan gave me a nice introduction there. Again, I'm a professor at the University of Texas, co-founder and CTO at Datum, which is a kind of tech-enabled, energy-focused data science education company. We've partnered with SEA to offer some of these courses along with them. And more specifically on my expertise and background as related to the topic we're covering today. When I worked at Sandia from 2004 to 2011, I was essentially a professional code developer, developing computer codes that would, engineering and physics-based codes to solve problems on the world's largest computers. That was mostly in C and C++. I picked up Python as a scripting language around 2011, and I've been using it ever since. And proficient in many languages, your typical engineering languages, Mathematica, MATLAB, C, C++, Fortran. But as time has gone on, I've found myself essentially only using Python, and then more recently a little bit of Julia. So Python is a very powerful language. It has a lot of great tools in the ecosystem. And I'm going to kind of give you an overview of our energy data science course here in the next slide, and then we'll dive into one lecture from that class to give you a taste of what the overall class covers. So right here is a list of, or a partial list of, what we would typically call the Python data science ecosystem. So of course it composes the language Python itself, but a lot of third-party packages that are used for array computing, tabular data type computing, and visualization. So Numpy is kind of the core array computing toolbox. Pandas is what we'll talk about today. It's sort of your drop-in replacement for Excel within this ecosystem. Bokeh and Matplotlib are visualization toolboxes. Jupyter Notebooks are a common format for data science, exploratory data science, a tool for exploratory data science and documentation. SciPy contains all the numerical algorithms that we would use. Panel is a dashboarding tool, and of course scikit-learn is probably the world's most used machine learning toolbox, and we do cover it at a very introductory level in the Introduction to Data Science course, and in the Subsurface Machine Learning course, it's used more extensively. In addition to that, we cover some software engineering stuff. So we cover Git and GitHub, as well as topics like continuous integration and other things that unit testing, other things that would be a true data scientist or software engineer would have in their toolbox. We cover those at least at an introductory level in the course as well. So with that, we'll, I guess the other thing that we do in the course is we use a project-based learning technique. And so along the way, as we learn all of those different modules individually, we work towards building a dashboard for data visualization and analysis. So let's see if this works. Instead of using the dashboard interactively live, I've just recorded a demo of me using it. So the idea here is that you can choose a state and a stock ticker for an operator. And once that choice is made, I think here I choose CXO, it will live update on the map all of the wells for that operator. So there are all the wells, and I zoom into those wells, selecting an API that will then plot the production histories for those wells. And you have also the option to fit, say, a type curve to that. So this, for some reason, is running a little bit fast to be useful here as visualization, but hopefully you get the idea of what we do. So we actually build this completely with open source tools in the class. The class is very hands-on. So you will actually, if you sign up for the class, you will actually build this tool using all open source software during the progress of the class. So with that, we'll jump into one of the lectures from the class, and that is on Pandas. Pandas is the data analysis library for Python, and for the most part, this lecture is standalone, meaning you don't need to know any other libraries to follow this, other than just some basic Python syntax. There is one caveat in that I do use a little bit of Numpy, which is again the array computing toolbox. So Pandas builds on top of Numpy, and it's a little hard to avoid it. So in the course of teaching the actual full week-long energy data science class, we would cover Numpy before we cover this lecture. Again, Pandas is kind of your drop-in replacement for Excel. So it's best used in what you could think of as two-dimensional data sets. So data where you would have labels across the top. If you're used to Excel, those labels are just alphabetical, right? A, B, C. Those are the column labels. In Pandas, we actually have the ability to give those labels names, and then we can operate on those columns via their names, which makes the code quite a bit more readable than anything you would see in Excel. So, in addition to the column labels, there are also row labels. Those row labels are usually just monotonically increasing integers, just like in Excel, 0, 1, 2, 3, 4, 5. But we also have the ability to assign any arbitrary label, and this becomes particularly useful when you have time series data, which we often do in petroleum engineering, or at least in production engineering, where you have you're analyzing production data. So you can actually label your rows with the timestamp of the production, and that offers some nice features for working with and organizing the data. So we'll start by just saying that, if you're familiar with the Python world, all of these third-party libraries that we use to do data analysis, you have to import them into the active namespace. And the way we always want to do that with Pandas is to say import Pandas as PD. And the reason that I take the time to even talk about why it's important to import Pandas like this is because inevitably you're going to find yourself going to the web to look for questions, either within the Pandas documentation itself or also on Stack Overflow, right? I mean, I've been a professional code developer for 20 years. Every day when I write code, I have a web browser open exploring documentation and Stack Overflow. So no matter how much experience we have, we find ourselves going out to the web for help. And what you'll see is that it's become idiomatic to refer to Pandas in code as PD. So when you go to, say, Stack Overflow to look for help or an answer to a question you might have, you likely will not even see the import statement in any code snippets. You'll just see the PD out in front of any functions or methods that are being used, and therefore, that's why I take the time to point it out here. So Pandas will almost always be referred to in code as simply PD. If you're familiar with NumPy, we often do the same thing with NumPy, where we say import NumPy as impy. So again, this is strictly for the reason for mentioning this is just to help you when you go out to the web and look for help in the Pandas documentation or on Stack Overflow. So Pandas has great ability to read CSV files. If it were the only reason you use Pandas, in fact, it might be just to read in CSV files. So in other words, if you were going to do some array operations on a single column of this data, it might be easier in some cases to use NumPy to extract the raw data in an array form and just use NumPy to operate on it. However, you probably still want to read it in with Pandas because it has, in this case, I'm only giving the file name and reading in the data set, but it offers a tremendous amount of options as to how to parse the data. For example, if you had delimiters that weren't commas, if you had other kind of header lines in your file and other things like that, it just offers a tremendous ability to parse CSV files and to do it quickly. Pandas has no trouble reading CSV files with millions of lines, tens of millions of lines. It can load them in a matter of seconds. So, and so in this case, I read in a data set. I have a data set called 200 wells stored in a CSV file. I read it in, and the default data structure in Pandas is something called a data frame. We often assign that to a variable DF in this case. In a data frame, you'll have columns and column labels as they're visualized here. In this case, I'm only printing off the first 5 rows of the data frame so that the DF head command by default prints off 5 rows of the data frame. Python is 0 indexed, so you see the 0 row 1, 2, 3, 4, those first 5 rows. Again, across the top, you have labels. In the lingo of data science and machine learning, you might call these features, right? So you have the features or the labels across the columns, and then the index are these integer numbers over here. And again, often these are just monotonically increasing integers, but we can also set the index to any value. And where this is most useful is when you have time steps. So we can actually refer to a row of data via its timestamp. In addition to reading CSV files, Pandas has built-in functions for reading Excel notebooks, for making SQL calls, and loading them directly into data frames. So it has a tremendous amount of ability to read various kind of 2-dimensional data structures that we store in files and read them into data frames in which then we can do operations on. So this data frame, DF, in the lingo of Python, which is an object-oriented language, data frame is an object. And objects have functions that operate on the data they contain. So in this case, describe is a function that operates on the data in data frame. And what it does is it actually automatically computes some summary statistics. So even though we're only, in the previous slide, we were only displaying the first 5 rows, you can see actually that there are 200 rows for all of the samples. So this data set has X and Y locations. Those are just latitude and longitude locations of some samples, along with this facies threshold, a porosity, permeability, and acoustic impedance values. And there are 200 samples in the data set, as you can see for all labels, there's 200 account. There's also, again, in this describe computing summary statistics, it automatically computes the mean, the standard deviation, the min, the max, and the different quartiles for each of these. So it's kind of nice to quickly get an overview of what kind of data you're dealing with here by just calling describe on the data frame. We can access parts of a data frame by their labels. And so in this case, if we only wanted to look at the porosity column, we can just refer to it via its labels with this bracket syntax. Excuse me, I'm a drink here. So you can use this bracket syntax to pull off only the column, and you see that it's printed to the screen also with its index. And again, this becomes more useful when the index has a meaning, like possibly a timestamp. We can then do numerical operations to this. And what makes this really nice, of course, is that the code becomes very readable when we refer to the columns via the labels that have some actual meaning, right? Versus, say, Excel, where your columns are just labeled A, B, C. And you have to continually, as you type equations, you have to continually kind of refer back to the column labels to understand what the code is doing. Here, it's very sort of explicit, right? This is the porosity column. Again, in most cases, you'll see me you'll see the head command tacked on to the end of most of my commands that we'll go through today, because I just want to print off the first 5 columns. To print off more than that is usually unnecessary if you're just inspecting the data. If you wanted to pull off multiple columns to do operations on, then you could pass in a Python list of labels. So in this case, I could pull off the porosity and the permeability columns from that total data frame. Remember, the total data frame also has the X and Y locations, the facies threshold, and the acoustic impedance. In addition to referring to the columns, we can actually refer to the rows, and we can pull off a subset of the data frame in this way with the member function load. So on the data frame, I'll call the loc function. The first argument to this function is a slice syntax. So again, if you're familiar with Python, this slicing syntax just simply means take rows 1 to 2. I could change this to say 1 to 4, and it would pull off those rows as well. So in this case, I'm pulling off the first 2 rows. I'm sorry, the 1 and 2 indexed rows. Remember, Python is 0 indexed, so there's a row above 1 that is 0 indexed, as well as the columns porosity and permeability. So this allows me to subset the total data frame. And of course, then I could go on and continue to do calculations on this. I can also use this so-called slicing syntax on the labels themselves. So it's fairly obvious to say that, you know, this is 1 to 2 or 1 to 4. But what this does is take from porosity to acoustic impedance. If you went back and looked at the original data frame, you would see that the column labels are porosity, permeability, and then acoustic impedance. So in this case, we can use this slicing syntax with the labels themselves. While the code is certainly more readable when you use the column labels, you can also refer to them by their integer location from right to left. So the first column would be integer 0, second column integer 1, and you can refer to those via the iloc function. So in this case, I'm pulling off, the syntax is a little bit different here in that it uses Python list style slicing. And so it doesn't include the last value. So to say from 1 to 3 here actually just pulls off 1 and 2. Same thing for the columns. To say from 3 to 5, it just pulls off the third and fourth column and excludes the fifth. So in this case, that would be the facies threshold and the porosity along with the rows 1 and 2. Again, these are just operations to take subsets of the data frame. If you're familiar with NumPy and doing, you know, NumPy is the array workhorse in the Python ecosystem, meaning if you want to do calculations on arrays of data, you know, so say you had an array of data X and you want to do an element-wise multiplication to an array Y in NumPy, if the array X is a NumPy array, if the array Y is a NumPy array, then the syntax is simply X times Y. You don't have to write a for loop, which you would have to do in a lower level language or even in pure Python itself. Again, if you take the full energy data science course, we cover NumPy in detail. In this case, if you want to pull off the NumPy array for the porosity values, then you just use the values command and or the values attribute, and that will give you the underlying data. So you notice now the index is missing. It doesn't print to the screen in that 2-dimensional format where you see the row label that is the index. So in this case, it's just the raw underlying data, and we could then use that to do computations. We can do transformations of our data frame. That's what the next few slides will talk about. One thing we might want to do is rename our columns, you know, to make them something possibly shorter. For example, if we wanted to rename facies threshold 0.3 to just facies, we would use a Python dictionary. So the syntax in a Python dictionary is always keyword value, keyword value. So in this case, the keyword is the old name, the value is the new name. So we want to shorten these names, permeability to perm, acoustic impedance to AI. And the in place function out here, keyword argument out here on the end simply means to make these changes in place in memory. In other words, do not return a copy of the data frame with the labels replaced, leaving the original data frame unchanged. In this case, we're going to actually change the original data frame. So those old labels are effectively gone from our data frame. We can add new columns to the data frame very easily. So in this case, we're going to add a column called 0. For that, we're going to use the NumPy zeros command. That just creates an array of zeros. that we're going to then stick into the data frame in the column location 0. And so after we run this first line and then print the second line, just prints the first 5 rows, you get this 0 column out here, as well as the other columns. So just like we added columns, we can remove them. The command we use to remove columns is the drop command. So we can drop, again, we refer to the column by its label, 0. So we're going to drop the 0 column. In this case, we also have to specify the axis. So the default is axis equal to 0, which refers to dropping a row. I have an example of that coming up. In this case, axis equals to 1 means drop the column, right? So we're going to drop the column 0 along, the axis equal to 1 refers to the column. And again, we're going to do it in place. So here's an example of dropping a row. Now, in this case, our row label is just an integer. So, and the default axis is 0, which means drop a row. So in this case, we can just simply say drop the 1 row. And you see it's missing now from the data frame. In other words, the index labels go 0, 2, 3, 4, 5. And again, I'm just printing off the first 5 rows with the head command. We can sort just like you might in Excel. So in this case, I'm going to sort based on the column label porosity. I want it to be in descending order, and I want to do it in place. And in this case, now I'm passing n equal 13 to the head function to print off not just the first 5, but the first 13 rows of the data frame. And what you'll see is that the indices are jumbled up over here. There is a kind of this useless column in the data frame called unnamed, and it just refers to the same indices there. But nevertheless, you can see that instead of ordering them monotonically increasing like they were before, now they've been jumbled up, and that's because the porosity column has been sorted in descending value. So the highest value of porosity at the top to the lowest value. And all of the other columns followed that same sorting procedure, just like in Excel, if you wanted to do that. So if you wanted to reset that index, so if you wanted to be monotonically increasing, not all jumbled up, and that's why this column here is in the data frame, so that you can see what used to be row 38 is now row 0 after this call of reset index. So we're going to reset the index, again, doing it in place. In this case, the drop command ignores the fact that there was that missing row that we dropped and continues to just number them monotonically increasing from 0 to 1. So if you did not put the drop in there, this would say 0, 2, 3, 4, just like before. In other words, because we dropped that row that was originally labeled 1, we have to call this drop equals to true so that we get this monotonically increasing set of integer indexes. So in the lingo of machine learning, we often talk about feature engineering. That is, taking the features that we have and creating more meaningful features. Often we actually use machine learning techniques for this, like multidimensional scaling or principal component analysis. In this case, I'm demonstrating feature engineering with just very kind of dumb or simple examples. So for example, if we wanted a new feature that we would call the percent porosity, then we can just take the porosity column and multiply by 100, right? So here we created a new column called percent porosity that is just the percentage of the original porosity column. Of course, the nice thing about this is that, the equation reads very easily, right? I mean, we've taken the original column porosity and multiplying by 100. Again, this is sort of a uninteresting or meaningless feature, but if we wanted to create a feature that we would call perm-pore ratio, that is the ratio of permeability to porosity, we can just simply refer to the permeability column and divide by the porosity column. And this happens, the computation occurs element-wise across the whole column. And so this takes all of, the first index permeability and divide it by the first index porosity. the second index permeability divided by the second index porosity, and creates a new column that we call perm-pore ratio. And again, I'm just printing off the first 5 rows. We can also use some Numpy commands to create conditional categories. So in this case, we use this Numpy where command, which allows us to basically do a comparison. So what we're going to do is we're going to say wherever the porosity column is greater than 0.12, we want to assign that a label high. And where it's less than 0.12, we want to assign it to a value low. And then we set that we set the output of that, which would be just a NumPy array, to a new column in our data frame we would call porosity type. So here, and the rest of the syntax just shows you the parts of the data frame where this happens. So if I print off the first 3 rows, you'll see, in fact, that because the porosity is greater than 0.12, we get the label high. And we have to go down to the 165th row before we actually, before that condition is not true. And then we see that if we print off the first 3 rows, we see that the value low is labeled there. So again, this allows us to basically evaluate whether this is true or false across the whole column in one command, and then assigning high or low to it, right? So it's very compact syntax. We can do additional things. This is kind of more of the same. So in this case, what we're going to do is, instead of just assigning a high or low kind of string value, we're going to basically say if the porosity is greater than 0.12, the permeability is the permeability. However, if it's less than 0.12, we're going to cut off the permeability. So whatever the permeability value really is, we're going to reassign it to 0.0001 millidarcy. Right? So again, and then I just print off the first 3 rows so you can see, in this case, the permeability cutoff, this new column we created, the permeability cutoff is the actual permeability because the porosity is greater than 0.12. But if we go to the 165th row where the porosity is less than 0.12, now our permeability has been reassigned to 0.0001. So we can also apply any generic functions to our data frame. So at the top here, I have a Python function that I call Cosine-Kármán with threshold, and it takes an argument phi and a parameter m. M is just a so if you're familiar, most of you I saw, or more than half were geologists, and the other half petroleum engineers. All of that group should certainly be familiar with the Cosine-Kármán relationship, which estimates permeability as a function of porosity, and that function of porosity is what you see here. So phi cubed divided by 1 minus phi, that quantity squared, and then there's a proportionality constant m that we usually fit to the data set, and then this gives us a prediction of permeability. However, in this case, I'm using that same kind of threshold logic that we used before to say that if the porosity is greater than 0.12, then we want to use the Cosine-Kármán model. Otherwise, we're going to assign it to 0.001. The thing to note here is that while this function is quite simple, this function could be 10,000 lines of code, and the way we would apply it to the data frame would be identical to the way we'll do it here. So this allows us to have, arbitrarily complex functions that we apply to columns of data. And this is where Pandas really outshines Excel, because if you the longer your equation is in Excel that you're applying to a column of data, it becomes more and more unreadable. And again, you're forced to constantly refer back to the column labels to try to understand what column of data you're working with and other things like that. It also doesn't lend itself to testing very well. So one of the things we discussed in the Energy Data Science course is unit testing and code quality and reproducibility. And production quality code should all be tested. So there should be an automated test that calls this function with known inputs to produce known outputs. And those tests should be in place and run automatically in our code if we have, for what we would call a production quality code. This simple function is quite easy to test, or actually any complex function would be easy to test in this kind of framework, not so much, or basically not at all necessarily in Excel. And so the idea here is we have this function, which in this case is simple, but it could be complex. And the way we apply that function to a column of data is with this apply function. So we're basically going to take the porosity column, and with this apply, the argument to apply is a function itself. So Kozeny-Kármán with threshold, that calls this function, giving the porosity value as the first argument, phi, right? So porosity goes into this function. This thing is computed with m is specified as a value of 10. And finally, then you get what you have here. So this is the Kozeny-Kármán prediction of the permeability given that porosity. Now, this is not necessarily, the value of 10 is not meaningful. I didn't actually fit it to any data or anything like that. So these numbers over here may not really make physical sense, but I'm just applying this function to the porosity column to get these results. Now, I guess I didn't go far enough down the data frame to show that you would actually get this 0.001 in some locations. So Pandas has a lot of built-in features for handling missing data, and this is almost always our data sets are messy. There's often missing data or outliers that we want to replace, things like that. So in this case, our original data frame didn't have any missing data. So what we're going to do is actually set a missing value. So what we're going to do is use the at command. So at is very similar to loc and iloc in that you're subsetting the data frame. The difference is that at refers to a single value, right? So where loc and iloc can refer to many columns and many rows to take a large subset of the data frame, the at function is specific to one value. So in this case, I'm going to take the one index row in the column porosity, and I set it to none. And what that does is, if I set it to none, it's automatically going to convert to the appropriate not a number type for that column, right? So this column is a bunch of floating point numbers, and the appropriate missing value for a floating point number is a nan, right? Not a number. If this were a column of timestamps, then what you would see is like NAT, not a time. It's a built-in missing value for a timestamp in Pandas. There's also built-in missing types for string values, like for high and whatever. I think in that case, you would just see NA if it was missing a string, right? So we're going to set a missing value in our data frame as if it was always there for whatever reason. And then we're going to look at some functions that allow us to identify those. One of those is null. So what we can do here is if we call data frame porosity is null, that gives us an array of trues and falses. It's going to give us a false where the data exists and a true where it's missing. And we can use that array of trues and falses. So in this case, what's inside the brackets would produce an array with 199 falses and one true. And that one true is at the one index row, right? And what I can do is use that true false array to index back into my data frame, leaving me or presenting me with only the row where the missing data was. So if there were multiple rows that had missing data, then you would see multiple rows printed here using this kind of syntax. In this case, I only had one row in the whole data frame with any missing data. And so that's all you see. There are built-in functions for dropping rows with missing data. It's not often that we want to just get rid of the missing data or get rid of the whole row, because even in this example, even though the porosity value was missing, all of the other values were there. And so it's likely we would want to drop that row completely, but rather replace that missing value with something else, like perhaps the average of all or the median of all of the column. And there are built-in functions for doing those kinds of operations. In the lingo of data science and machine learning, that is called data imputation, deciding what to do with missing data. In this case, we're just going to drop that row. The command we can do for that is drop NA. So we don't even have to specify the row. Simply saying drop NA drops any row that has any missing data. So we can, in the examples I've shown so far, we read in the values from a CSV file. And again, I mentioned we can read in values from Excel files, from SQL commands, but we can also create data frames from scratch on our own. The way we do that is just in this case, I'm just creating basically some random values of porosity and permeability, or random values of porosity, and then using the Cozzini-Kármán relationship to compute the permeability. I then create a Python dictionary from that. So the keyword here is porosity, or the string label, and I'm assigning that the variable, which is a NumPy array of random values for porosity, as well as the permeability label and the NumPy array permeability. Then we can create a new data frame from that dictionary by simply passing it into the pd.dataframe command, and then we can do all the operations that we talked about before. So now we have a new data frame that I can sort the values on the porosity column with, for example, and that's what we see here. In this case, we can also, here's an example where we concatenate two data frames. So we're returning to our original data frame and creating two subsets. The first one is the rows 0 to 3 and the columns 2 to the n. And additionally, we create a new data frame from the rows 10 to 13 and 2 to the n. So those are the data frames DF1 and DF2, and you see those subsets here. We can use the concat command to concatenate the data frames along the rows. If we specify x is equal to 1, we can concatenate data frames across the columns. So there's an easy way to join data together. Again, much easier than trying to do it in Excel and copy and pasting from different workbooks or whatever. Another great feature about Pandas is its built-in plotting features. So a lot of data science is actually data visualization, just coming up with clever ways to visualize high-dimensional data sets. And we can quickly do that in Pandas with the built-in plot command. So if we have a data frame and we just call plot on it, it'll automatically do its best job to create a plot. Now in this case, it automatically plots the data versus the integer index, which is just a monotonically increasing set of integers in this case. So it creates this very unmeaningful plot. However, what we can do is we can set the index to one of the values. So for example, we could set the index to porosity, and then we call plot on it, and it plots the permeability against porosity, and you see it automatically generates the labels even for us. Now, if we didn't want to set the index like that for whatever reason, we wanted to keep the monotonically increasing integers as indices, we could also explicitly specify the x and y values as their labels, porosity and permeability, and we get this plot, right? So, and again, it automatically creates the labels for us and whatever. So this is kind of a very quick look, built-in way to do plotting in Pandas, and it allows for a built-in, some nice exploratory data analysis. In this last example, I used this scatter plot to plot the dots. The default is a line plot. Finally, we can write, just like we read data frames from a file, we can write them quite easily. In this case, we're going to use the CSV file. CSV files are kind of the standard for small data sets in the data analysis world. They're kind of the standard way to store your data. You can read them and write them much faster than you can write Excel files. And there is some limitations when you have multiple sheets in Excel files as to how you write them and other things from Pandas. So most of the time, if you're not going back to Excel for any reason, we just write it to a CSV file if it's a small data set. So we write it to this 200 wells out, and then here I'm just using the Unix head command to actually visualize the first 5 rows of that file. So you can see the first 5 rows of the file are, that data frame that we've been messing with this whole lecture. So it has the porosity type, the cutoff, the Cosini-Carmen column, and all of that, and all the data stored in there. So with that, that concludes this short lecture, and I'm going to go into a hands-on exercise.
And while John is pulling that up, I'm going to remind our attendees today to please type your questions into the question feature, and we will ask them at the end.
So what we're going to do here in the last few minutes, 5 minutes or so, is I think I need to lost my cursor due to the PowerPoint. There we go. Okay, so where we are now is we have a for this course, for the Energy Data Science course, we have an online classroom which you'll be given access to. In that classroom, you'll actually see, in this case, here's the full syllabus for the entire course, which includes the Pandas lecture that I just gave, but with more details. So while I gave it in a PowerPoint format, what you'll see here is a Jupyter notebook with a lot of information. So this reads more like a book. You can follow along. All of the same examples that I use in the slides are there, but this is an executable Jupyter notebook. This is Python code that we can execute. You'll be given access to our online classroom, and you'll follow along my lectures, possibly executing the code along the way. And then we have a series of exercises that we'll be working along the way. Now, so here's something you can do nice, rather quickly in Pandas, right? So the question is, you can read this if you want, but the question is, what are the 5 all-time highest producing wells for EOG in the state of North Dakota? Well, within our online classroom, we have the ability to pull public data. We have a database that's similar to, if you're familiar with, say, Drilling Infos or IHS Markets. We have an equivalent database, and we can pull data in real time from that database and to help solve these problems. And so if you were to go read the details here, basically the idea is that we have some information. So for example, what I'm going to do is show you some of the data that we're going to pull from. So I'm actually writing live Python code here. And this pulls from our database in real time. A typo there, it should be wells. So what this did was pull all of North Dakota's wells with the ticker EOG. And so what we're going to do is we're going to assign this to a variable, EOG APIs in North Dakota. And so this is what it looks like. And what the thing about this data frame is it has the API numbers for all of EOG's wells in North Dakota. So evidently there are 1,264 wells that EOG has in North Dakota. In addition to the API number, it also has the latitude and longitude surface holes, but we're not interested in those in this example. So we'll move on. Additionally, we have another database where I can pull the production by state for North Dakota. And let's take a look at what that looks like. This might take a few more seconds because what it's actually doing is pulling in every single month of production history for every well in North Dakota, not just EOG wells, right? So in this case, there's 1.29 million rows of data. We're going to store that in a data. We're going to store that in a data frame we'll call North Dakota production. Again, this is the production for every single well in North Dakota, not just EOGs, for every single month, right? Keep in mind, that's 1.29 million rows of data. can't even load it in Excel as fast as I was to pull it in the database, load it into my Pandas document here. Anyway, so I have two data frames. One has EOG's APIs, and one has all of the production in North Dakota. What I want to do is I want to find the intersection of these two data frames on the API so that I can pull out from the North Dakota production, I can pull out only the APIs that are EOGs, okay? And the way I would do that is I'm going to take the North Dakota production data frame. I'm going to pull off only the API column, and I'm going to use the Pandas command isIn, and I'm going to intersect it with this other data frame, EOG APIs in North Dakota. Now, what this results in is a Boolean array. It appears to be all false, but again, because there's 1.29 million in there are some truths in this data frame, and if we use that to index back into the overall data frame of North Dakota production, we'll get to see the ones that are true only. So in this case, there's 61,000 rows. Remember, that refers to there's like 1,200 whatever wells that EOG owns. Each of those have some months of production, and so that gives us 61,000 rows of data. Now these are only EOG's wells, okay? What we can then do, so if you notice, there is, for every API, there's a row for every month of production. So what we'll do next is we're going to call the Pandas command group by. So we're going to group by North Dakota production API, and then apply. Remember the apply, we can apply any random function to our data. In this case, what we're going to do is after we group them by API, that will give us, for every API, we'll have some number of months of production. We want to sum those months, okay, to get the total production. And so to do that, we're going to write a little function here. We'll use a Python Lambda function to do that. We'll cover this in the class in more detail. But we want to sum the volume of oil formation barrels. So if I do that, and look how fast that ran on 60, well, this did the whole thing. It found the intersection of the 1.2 million rows to get that down to the 61,000 rows, grouped them by API, and then summed all months of production over that. And so this is the total production for every single well that EOG has in North Dakota, sorted by API. So now if we want to define the 5 highest, all we have to do is sort like that. So now they're sorted in largest to smallest. And if you want to only see the first 5, well, we can just use our head command. And there we have it. So again, what I like to do here is kind of break this. In Python, if you surround any row with parentheses, you can break it into multiple lines. And so what I like to do with this is break it into multiple lines, kind of like this, so it's easier to see what's happening. Now, if you took our class, you would work this on your own, and I would help you. We have other examples as well, and examples for every module that we cover of hands-on coding. So again, if I run this, that's the result, but let's recap what we did. The first line finds the intersection of the two data frames. One has all of the production for all of the wells in North Dakota. The other has the API numbers for EOG's wells. We find the intersection of those two. Then we group by API number and then apply a function that sums over all months of production. That gives us the total production for every single well that EOG owns in North Dakota. Then we sort them by that by the result of that, right? We sort it by this number, the production, from highest to lowest, and then the final thing is to just print out the first 5 rows. And so that's how quickly we can answer that kind of question in Excel. And again, this is all about data science, is trying to answer these quickly, use statistics to make inferences about data, statistics and visualizations to make inferences about data. And we end up a lot of times asking ourselves these kind of what if questions, or like in this example, what are the 5 highest producing wells for EOG in North Dakota? By the way, we could change this to the nice thing about this is we could change this rather quickly to say Noble in Colorado. And if I do that, then run these. When those complete, that second line is quite large because it's pulling in all of the production in all of the wells in Colorado. So from our database, it does take a few seconds. But when that continues to run, we'll get the answer to that question. So I think with that, I maybe went 5 minutes into the question and answer period for this webinar. But if anybody would like to answer any questions. So there's the results. Those are the 5 highest producing wells for Noble in Colorado. And we could go on and change this to basically any state and operator we have and answer this type of question. So with
Great.
that,
So I'd like to
webinar and happy to answer any questions in the time that remains.
Right. I'd like to remind our audience that they can type their questions into the question feature in the GoToWebinar dashboard. You are muted, but you can put your questions there. And I want to remind everyone that you will receive a link to today's webinar recording, an evaluation form, and you'll also get a link to register for John's class on Introduction to Data Science and Python that's offered in a live online format in August 10th through 14th. So first question, what kind of problems generally do we face in geoscience that we can use these tools for energy data science to solve?
Yes. So again, basically anything you can do in Excel, you can do in Pandas in a much more robust way, right? You can create higher quality plots. You can analyze the data faster. Again, right here in real time, I found the intersection of 2 data frames. One of them had 1.2 million wells. You can't even open a file in Excel that has 1.2 million wells, much less run the whole analysis like I did in a matter of seconds. So, basically, you can think of Pandas as the drop-in replacement for Excel, but you're just going to be able to have more readable code, more testable and reproducible code, faster code, and higher quality plots and output.
So what if there's not a number, NaNs, in the data?
So the correct thing to do would be to handle it before you analyze it. So you would do something with it, replace the NaN with something. Depends on if it's time series data, then you would probably interpolate the value above and below it. If it's something like porosity or any kind of petrophysical data, you might just take the average or the mean, or the mean or the median of the total set and replace it with that. So the correct thing would be to handle the NaN before you analyzed it, before you did some computation, before you did some plotting. If it's a computation, an NaN times a number is going to give you an NaN, right? So if you try to multiply 2 columns, one of them had an NaN, the result is going to have an NaN there. For plotting, it'll just ignore it. It'll just won't plot that data point. So if you have an NaN there and you try to plot it, it's just going to ignore that data point. You won't even see that in the plot.
So it's easy to share Excel files with others. How can we do that with Python?
Again, the kind of standard in the data science world for small data sets would be CSV files. Those are just text files, comma separated value files. You can take any Excel file and export it to a CSV file from Excel. You can also, I don't cover it here, but you can read in Excel files into Pandas as well. So if Excel is still your preferred, you know, mechanism of storing data, then you can still do that here. Now, if it comes into like not just sharing the data itself, but rather the analysis and the code, well, that's what we do here with these so-called Jupyter notebooks, which we can turn into. We can export these Jupyter notebooks into many other formats. I'm not sure. Are we still sharing my screen?
Yes.
And so if all I did was go to the file menu. All I did was go to the file menu in my Jupyter session here and say File, Export Notebook as PDF, and then what that produces is this nicely formatted, you know, PDF that you could share with your colleagues as well. So there are many options. We cover that. We cover all of that kind of aspect in the energy data science course, is how to, you know, kind of share the code itself as well as the results of any analysis.
So there are 2 or 3 questions about access to the data libraries for drilling inflow and IHS. How do you work through that during your class?
So there must have been some misunderstanding. We do not use drilling info or IHS. We have our own database that's sort of equivalent to theirs. I mean, they're just wrote web scrapers, scrape the web. We wrote our own. We have the same thing. We regularly compare our data to theirs. It's at least as high quality as theirs, if not better. In many cases, it's exactly the same data. So we have that built into our classrooms. When you take the class, you're going to get access to this online classroom, classroom.datum.io, and it's simply through these commands. And I know I didn't cover them in detail here as a sort of what's happening behind the scenes, but we do in the class. We use a package called intake. It's another Python package that essentially hides the SQL calls that are being made into our database and allows us to import them directly into Pandas data frames. So again, we have our own database that's equivalent to drilling infos, and you don't need an API key or anything like that. All you need is access to our classroom, which we will give you upon registration of the course.
Great. We've got several questions. I think we're going to run out of time, but you will be able to answer those later via email. So this is the last question. Can you explain the step in the exercise where you brought the Indy production data frame back in front of the ISIN function?
So we have a data frame. In this case, we're only using the API column of that data frame. That's North Dakota production. Again, reminding you that this is the production history for all wells in North Dakota. And the only label there is the API number. This finds the intersection of that with the other data frame that has the API numbers for that we know are EOGs. So again, if I run this part alone, it produces a Boolean array, trues and falses. Now in this case, it only prints the first 5 and the last 5, so you don't see the trues, but they're in there. They're in the ... Okay, they're somewhere in there. And so we can use this Boolean array of trues and falses to what we subset, again, the North Dakota production data frame, taking only the values where they're true. The true values correspond to the APIs that are owned by EOG only. So if I run that, then I get EOG's wells only in the data frame, and you can see there is some missing data there. You can also see that the indexes are not necessarily, you know, the first 6,000 are missing. That's because those weren't EOG's wells in our original data frame. So just the wells that you see here are EOG's wells, and then we can go on and continue. The next line is where we group them by API, sum them over all months of production, sort them, and then print out the first 5.
Excellent. So I'm sorry we couldn't get to all the questions today, but we will reply via email. Thank you so much for your enthusiasm. Later today, you'll receive a link to the recording of today's webinar, an evaluation form, and a link to register for John's class, Introduction to Energy Data Science in Python, that's offered live online in a public format August 10th through 14th in the mornings. Thank you, everybody. Goodbye.
I'll just do the best.
Bye.